Serverless is one of those ideas that sounds revolutionary when you first hear it. No servers, no infrastructure. Automatic scaling. Pay only for what you use. If you listen to cloud marketing long enough, it almost sounds like architecture itself disappears. The reality is, systems don't eliminate complexity. In systems, complexity never disappears, it relocates. Serverless didn't remove infrastructure complexity, it moved it somewhere else. The event structure, the security model, the cost behavior of the workload, and the organization operating the system. When teams adopt serverless, the goal is usually very pragmatic. They want to remove operational friction. Running distributed systems today often means running clusters, container platforms, scaling rules, monitoring systems, and patch pipelines. Serverless promises to remove most of that layer. Developers deploy functions. The platform runs them. Scaling happens automatically. And economically, the hope is simple. Stop paying for machines that sit idle most of the time. The architectural pattern behind serverless is also straightforward. Instead of long-running services, the system is decomposed into small execution units. Functions run briefly, respond to an event, perform work, and then stop. A request arrives. A function runs. It emits an event, writes to a queue, updates a database, or triggers another function. Instead of service-to-service communication, the system becomes a chain of events and reactions. Client to gateway, gateway to function, function to event, event to another function. Infrastructure didn't disappear. It moved into the platform layer. And that changes how the system behaves. Several forces push organizations towards serverless. The first is operational complexity. Running microservices often means running infrastructure platforms to support them. Containers, clusters, scaling systems, deployment orchestration. Serverless removes much of that operational responsibility. The second force is workload variability. Many systems experience bursts of activity followed by long periods of inactivity. Serverless aligns well with those patterns because compute appears only when work exists. The third force is economic pressure. Idle infrastructure is expensive. A server running at 10% utilization costs the same as one running at full capacity. Serverless replaces capacity planning with execution-based pricing. Instead of paying for availability, organizations pay for actual work. But when serverless systems grow, new dynamics appear. The first is function proliferation. Small execution units multiply faster than architectural understanding. A system that once had a handful of services can easily end up with dozens or even hundreds of functions. The second dynamic is event chain expansion. Functions trigger other functions through events. The system stops being a service topology. It becomes an event graph. Understanding how work moves through the system becomes significantly harder. The third dynamic is permission proliferation. Each function needs its own permissions to access resources. Security stops being a boundary. It becomes a distributed property of the system. At this point, many teams assume serverless improves security. Smaller components, more granular permissions, smaller blast radius. In theory, every function gets its own identity. In practice, organizations cannot govern hundreds of identities. So organizations begin reusing security boundaries. Multiple functions share the same IAM role. They share network policies. They share outbound access paths. From an operational perspective, this simplifies governance. Decomposing compute is easy. Decomposing trust is much harder. Architecturally, the system looks decomposed. The trust zones often are not. If an identity is compromised, the impact may spread across many functions that share that boundary. The diagram shows isolation. The security model shows shared blast radius. Serverless also changes the economics of a system, and this part is often misunderstood. The serverless pricing model is optimized for one very specific scenario: eliminating idle compute. If your workload is event-driven and spends a lot of time waiting, serverless can be extremely efficient. But if the system has a constant baseline workload, the economics change. If functions execute continuously, serverless becomes baseline compute with a per-execution tax. At that point, containers or VMs are often cheaper. Serverless is not universally cheaper. It is economically optimized for workloads with large idle gaps between bursts of work. The structure of the system also changes. Traditional architectures were shaped by infrastructure boundaries. Servers, clusters, networks, those elements defined how systems were organized. The architecture becomes defined by three structures operating together: the event graph, the permission graph, and the platform service graph. Infrastructure disappears from view. The system becomes structurally denser. There is also an organizational dimension. Because decomposing compute into functions is easy, designing governance around those functions is not. Compute decomposes quickly. Governance decomposes slowly. Serverless reduces infrastructure operations, but it often increases coordination between teams. So, what kind of system does this architecture actually produce? On the positive side, these architectures can scale extremely well. They eliminate idle infrastructure. They enable rapid deployment of small pieces of logic. But other characteristics appear. Event graphs become difficult to reason about. Permission models become distributed. Security boundaries are shared. Costs depend heavily on workload patterns, and architecture decisions become tightly coupled to platform capabilities. The system's insight is simple. Serverless did not remove complexity, it relocated it. From servers to events, from network boundaries to identities and permissions, from infrastructure management to platform constraints, and from capacity planning to workload economics. The system is still complex. It is simply complex in different places. Systems thinking simply shows where the complexity went. Good architecture is not about removing complexity. It is about deciding where the complexity should live.